I want to start with introducing a new idea. We've been making graphs of position versus time, and we've made a few of those. We'd have x in meters on the vertical axis and t in seconds on the horizontal axis. And for constant velocity situations, the equation, or the equation of motion would graph as a nice straight line on there. So that's constant velocity. And our general form of the position versus time graph ends up giving us something that looks like this. X equals x naught plus v sub x times t. We've been able to use that. Sometimes we didn't put a subscript on here. Sometimes we did a chase problem where we had subscripts of 1 or 2 on here because we had 2 different objects. But that's what we had. Now I'd like to introduce the idea of making velocity versus time graphs. We can have something that looks like this. We'll have velocity in meters per second now. Of course, you could have all sorts of different units for velocity, but we'll generally stay metric here and do meters per second. And time in seconds on the horizontal axis. Now, with a graph like this, if we had a situation where we have constant velocity, the graph is not going to be particularly interesting. It's just going to be something like that. It's going to be a flat straight line. However, there's something interesting that comes out of a graph like this, and that is that, let's suppose you pick some time interval from t1 to t2. Well, big deal. We've got this constant velocity equation in here, except here's something interesting. Okay, here's our value v, and let's just call it v sub x, and that's where it hits the vertical axis as well. But v sub x times delta t is equal to the displacement. And that's basically distance equals rate times time. Well, in this case, we've got v sub x times t2 times delta t in this case. We can just label it as such. That's displacement. Okay, that's the area under the v versus t graph. So keep that in mind. Displacement. And displacement is a quantity that can be positive or negative depending on which direction the thing happens to be going. If you brought your velocity down so it was a line under here, it would graph as something going in that direction on an x versus t graph. But you could have a negative displacement as well, but it equals area, we'll say under, because sometimes it might be an area over, but you can have a negative area. You'll find that out in calculus. Under a v, I'll call it velocity, spell it out here. Velocity versus time graph. Okay. So that's a situation with constant velocity situations, and it may seem just kind of a weird idea or something like that, but let's start playing with the velocity. So what if we had, actually I'm going to try rotating paper here and see if it still works. I think that works. I made a pen mark down here to a place I shall not pass, so that, because I noticed on one of the videos I was writing down below the mark where you couldn't see it anyway. So anyway, let's make a velocity versus time graph, and I'll leave the units off here. This is just going to be v versus t. And imagine that we had a changing velocity. So this would be something that at time 0 it was actually looks like a negative velocity, at least if this is the origin, and then it becomes positive, and it gets more and more positive as time goes by. The velocity is increasing. That's something that we tend to call acceleration, except for us, acceleration will have a broader definition. We could also have a v versus, can't see that, v versus t graph, where the velocity is doing something like this and maybe continuing on into negative values. Okay, this is another changing velocity here. Okay. Anytime you have changing velocity, you have acceleration. And I'll give you a verbal definition of acceleration first. Acceleration in physics has a very precise meaning. It is the rate of change of velocity. Now, we've had a rate of change of something before. Velocity is actually equal to the rate of change of position. Anytime you've got a rate of change of something, you end up with a mathematical relation that looks like this. For velocity, we had delta x over delta t. This is the rate of change of position. Delta x is the change in the position. When you divide it by the time interval in which that occurs, you get the rate of change, how rapidly that thing is changing. And that's what velocity is when we're talking about position. For acceleration, which by the way we'll use the letter A for, that's the rate of change of velocity. And it'll be delta v over delta t. We could have a negative velocity if our delta x happened to be negative. We can have a negative acceleration if our delta v happens to be negative. Now, we're still studying one-dimensional motion here for the next week or so. And so in one-dimensional motion, a negative acceleration just means something is moving, or the velocity is changing in such a way that either if it's moving in the positive x direction, it'll be slowing down. If it's moving in the negative x direction and accelerating, it's speeding up in the negative x direction. So that's a way that you can have negative acceleration. So our physics definition of acceleration is any time there is a change in velocity, there is acceleration. So speeding up or slowing down is acceleration as far as we're concerned. We don't need to worry about the term deceleration, although we'll occasionally use it if something is slowing down. We can just call it negative acceleration if we want to. As soon as we start considering two-dimensional motion or three-dimensional motion, actually in this class as far as we go is two-dimensional motion, your velocity can also change if you change direction. And so we add a third way that you can accelerate. You can accelerate if you speed up, if you slow down, or if you change direction. And in fact, one of the types of acceleration that we'll study here before too long is the type of acceleration that occurs in circular motion. We call that centripetal acceleration. Not centrifugal, but centripetal. So that's some basic ideas about the definition of acceleration. As far as the units of acceleration go, let's do an example. If a car accelerates from rest, that's code for velocity of 0, to 60.0 miles per hour in 11.5 seconds. Okay, when I first moved to Moses Lake, I had a 1974 Plymouth Valiant, and it might have been able to do that. I'm not sure. It was kind of a beater, but I only paid $350 for it, so it was worth every penny. Let's see. Anyway, at 11.5 seconds, what is its acceleration? This happens to be 26.8 meters per second. And so we'll live with that. Okay, so anyway, the acceleration is going to be delta V over delta T. This is my equation in variable form, the way you should always start a problem solution. And delta V in this case is going to be, I'll just call it V final minus V initial over delta T. V final was 26.8 meters per second minus V initial was 0, started from rest. That's code for velocity equals 0. And then we did that in 11.5 seconds. Okay, so that's just a calculation to be done. And I get about 2.3. On top I've got meters per second, and on the bottom I've got seconds. And if you were taking this class in Britain or various parts of the world, the way they would express an acceleration is to call it meters per second per second. And what that tells you is that each second that passes, the velocity will change by 2.3 meters per second. So it'll increase by that. So after 1 second, the car might have been going 2.3 meters per second. After 2, it might have been going 4.6, something like that, if the acceleration was constant. What is its, I should say, average acceleration? Because we don't actually know what it was doing in between times here. It may not have been accelerating at a constant rate. So we actually calculated an average acceleration. So I could have put an AVG down here for that. In this class, for the most part, we're going to study situations where the acceleration is either 0, which moves it into a constant velocity realm, or it's constant. And that's about as complicated as we get, except for one type of motion, which is simple harmonic motion, where something's bouncing up and down on a spring. That's got more complicated acceleration, and we end up with kind of interesting equations of motion in that case. But anyway, there's an acceleration for an old car. Now, if it got from 0 to 60 miles an hour in, say, half of this time, which would be about 5.75 seconds, it would have double the acceleration, 4.6 meters per second per second. By comparison, there's a number we write with a lowercase g, and this is the acceleration due to gravity. It actually represents the magnitude of the acceleration due to gravity. It's, if you hold a rock out and drop it from your hand, it'll not be affected much by air resistance, at least if you're only dropping it from as high as your hand is above the ground, and it'll fall at about 9.8 meters per second per second. Now, I mentioned that that meters per second is the way they would express things in Britain and much of the rest of the world. In the United States, for some reason, we do something a little different. We look at that meters per second divided by seconds on the bottom, and we think of that seconds on the bottom as being divided by a 1. When you divide a fraction by a fraction, you invert and multiply, and you get meters per second times 1 over seconds. multiplying the m by the 1 on the top doesn't do anything, but you end up with meters per second squared. And that's the way we usually express an acceleration in the United States. If you were doing this in miles per hour, you'd have miles per hour second, and so that'd be kind of confusing. It might be better to think of it as, yeah, just miles per hour on top and seconds on the bottom. But meters per second squared is our usual unit for acceleration. And so that's an ancient car. I've read about newer cars that could do it in a fourth of that time or so, something like that. But if you do that on a city street or something like that, you might attract the attention of those people with those pretty little red and blue lights, and you might not want to try to quadruple that acceleration here. Okay, so that's just a real simple acceleration problem. Let's go back to a velocity versus time graph. Velocity on the vertical axis and time on the horizontal axis. And this could be time in seconds or anything like that, but I'm not actually going to worry about that much. I'm going to have a graph where at time 0 the velocity is not 0, so this is our origin down here, and I'm not even considering negative stuff right now. The equations we're going to end up with will work for just about any time. And so this could be v0 here, and we'll just consider going from v0 to some later time t. Now, when we had a nice horizontal line, it was easy to calculate the area of that, and the area ended up equaling the displacement. Well, that turns out to be the case whether you've got a nice constant velocity or whether you don't have a constant velocity. This area, it's kind of an area, it's not square meters, it's an area under the graph, will equal the displacement. And by figuring out what that area is, we'll come up with an expression for the displacement that involves the initial velocity, the time that's passed, and the slope of this graph. And the slope of this graph, that's equal to delta v over delta t. It's a constant slope. That's the acceleration. Well, let's see. How much is this going to be here? Let's calculate the area. That's going to equal the displacement. This is an abstract concept. Try to get a handle on that first by going back to the constant velocity thing and thinking about that. So the area is equal to this displacement. That'll equal delta x, which in this case is going to be x minus x sub 0, because we're starting from the 0 time here. Okay. Well, what have we got there? We've got a trapezoid. Okay. Now, if we're going to find the area of that, we have to know the height that we've got up here. Well, turns out if we've got a constant acceleration, the equation of this line is actually going to be v0 plus at. Okay, that's going to be the height up here. Okay, we've gone over a time t there. This will equal v0 plus at. So far, I'm just playing with linear equations. Well, what's the area here going to be? Let's figure it out. The area is going to equal delta x. We've got a rectangle here that's going to have a height of v0 and a length of t. So it's going to equal v0 t. And that's just the area of this rectangular part down here. What about the triangle? Well, that's going to have the area of a triangle is 1/2 the base times the height. The base is t. The height is going to be v0 plus at minus v0. Oh, that sounds like at, doesn't it? I think. But I'll write it out that way. v0 plus at, that's the height at the top, minus the height at the bottom. At any rate, we'll end up with v0 t plus 1/2 at squared. And that's pretty interesting. Okay, that means delta x is x minus x naught. So x minus x naught equals v0 t plus 1/2 at squared. X is equal to x naught plus v0 t plus 1/2 at squared. This is the position versus time equation of motion for constant acceleration motion. And that's a big deal. However, for constant acceleration motion, this isn't the only equation of motion. We also have this one. And so we have v equals v0 plus at is a second equation of motion. That's for velocity as a function of time when you have constant acceleration. And then there's a third one, and that third one is what you get if you solve this equation here, the velocity equation for t, because this is easy to solve for t. You just get v minus v0 over a is equal to t. That's a v there supposedly. Okay. You take that t and plug it in down here for those t's, and you get a third equation out of that. I'm just going to write it down here. It's kind of scary, but it looks like this. V squared minus v0 squared equals 2a delta x. And that delta x will be x minus x naught. So you can think of it that way. Okay. Well, that's an equation that doesn't even have time in it. Every once in a while, you'll get a problem where it just asks you, how far does it go? It's got this initial velocity, this final velocity, that's what the v would be, and the acceleration is this, how far does it go during that time? And you can use this equation for that. So that's a third equation of motion for constant velocity. Now, anytime you read a problem and it says constant velocity, the first thing you should do is write down this equation of motion, this one, and then look at what you're given and see what you can figure out from what you've been given. And you can do a lot by just starting each problem solution that way. Also, these equations work in the situations where you have constant velocity, because what happens if the velocity is constant, there is no acceleration, and so actually this equation becomes useless in that case, this bottom one. But if there's no acceleration, then this at term, a is 0, this part vanishes and you get v is v0. Okay, it's always v0 because it's constant velocity. This equation here, the a is 0, so this last part vanishes here, and you just get x equals x0 plus v0 t, or vt is what we've been calling it. So this works for that as well. So now we know a little bit about acceleration, and we know what the constant acceleration equations are. And so it's time to start solving problems.